My daughter just moved to Texas, and she's teaching me Texan. And I learned that y'all is singular and all y'all is plural. Anyway, I grew up in Canada, but I grew up in the southern part of Canada, so we have a lot in common. How y'all been, eh? So I thought we'd go through a 1,000 years of building Enclosure Evolution to set the stage. 1,000 years ago, we built things entirely out of rocks. This is a church in Ireland, and the roof is rock, the walls are rock, the foundations are rocks, the rocks are rocks. The overall thermal resistance 1,000 years ago was R2. About 500 years ago, we began to add thatched roofs, mostly for rainwater control. The oriented nature of the fibers, surface tension, gravity allowed for a magnificent water control technology. In fact, we use this approach of oriented fibers and surface tension and gravity below grade in drainage mats, and it's the most common water control method in curtain walls above grade. Anyway, the overall thermal performance improved to R4. 350 years ago in Middle Europe, we began to see post and beam construction and wattle and daub. Wattle and daub is a precursor to a modern stucco. The wattle was woven branches that eventually evolved into an expanded metal lath, and more recently a e-glass matrix. And the daub is now a multi-component polymer modified cementitious rendering. The big innovation, however, was that we began to get air cavities, air spaces, and that dramatically. 250 years ago, heavy timber construction. This is log cabins, approximately R8. 100 years ago, my alma mater, the University of Toronto, the Haltane building, single pane glass, which was R1, but less than 10% of the building enclosure was glass. Approximately 90% of the enclosure was 36 inches of mass, and the average thermal resistance was R8. 1972, double glazed, non-thermally broken aluminum curtain walls are, you know where we're going, don't you? R1.5. In 2005, a LEED award-winning building, double glazed, thermally broken aluminum curtain walls are R2. So in 1,000 years, we've gone from R2 to R2. Are there any architects here? I'll speak slowly and use small words, and you can explain it to the engineers later. What is singularly the most expensive part of the building enclosure? Glass. And what is singularly the worst thermal performing? So if you want a really expensive building that doesn't work, use lots of glass. All right. Now, there's a reason that we don't let engineers design buildings. That's because they'd have no glass. And so we need a balance between the engineer and the architect, and that requires judgment. And one of the things that I've learned, I'm now in my late 50s, and that is I'm going to argue in favor of beauty over energy. I think that in order for buildings to last a long time, which I think is a very good thing, because I think that's the ultimate definition of sustainability, is people have to take care of them. And I've discovered in all of my years that people don't take care of ugly things. Ugliness is not sustainable. People will only take care of buildings that are beautiful, buildings that people want to live in and work in, and only then will they take care of them. And so I'm always willing to give up energy for beauty. And like anything, if we begin to focus on one element over the others, we get ourselves into a great deal of difficulty. So I'm standing before you as an engineer arguing not to give up the beauty. Now, if we end up with a beautiful building that's going to be around a long time, we've created a machine that needs to be fed resources over its useful service life. So it behooves us to have that machine ultra efficient. And there's no contradiction between having a beautiful building that's energy efficient. But don't let the energy blind you to what the function of the building is intended to be in the first place. So if you have a choice between energy and beauty, take the beauty. Take it from an old middle-aged guy who's kind of figured this out. It's always nice to look at a beautiful building. Now, architects, you're giving us the beauty, but you're also giving us buildings that don't work very well. So I think it's important that we apply some of the physics. All right, one more example. I think you all recognize this. This is a baseboard convector. And let's look at it more closely. It's an incredibly efficient heat exchanger. We have a copper core with aluminum fins. Let's look at it even more closely. And then let's orient it correctly and compare it to this award-winning building. And this is the Aqua building in Chicago, and it was designed by Jean Gang, and she won a MacArthur Award. And here's the here's the infrared. And I called. I mean, I was so irritated. I called, and of course I couldn't get through to the great woman because Joe Lstiburek, who the hell is that, right? And so I got one of her lesser architects, and I said, so this is a LEED building, is it? He said, well, where's the insulation? I mean, you have glass and you have concrete. Well, there's lots of insulation. And I said, well, where? Well, we have an R11 radiant barrier paint on the concrete. That was the right response. I was very concerned that, okay, let's do this again so that we're all on the same page. The answer was, well, we have an R11 radiant barrier paint. Thank you. I said, well, there's a bridge in Brooklyn that's for sale. We could put it in some swampland in Florida. Are you kidding me? I mean, this passes for, well, okay. So, but it got its LEED point, and I said, well, where's the bicycle rack? Isn't that what makes a building LEED? So I don't get invited to those conferences anymore. Apparently, I have an attitude problem. But it's not just this building. I mean, I went through my hometown of Toronto, and I have no life, so I have an infrared camera. Late at night I drive the streets, taking. There's a bad cable TV show in the works there. Night Stalker. I mean, look at this. I mean, you're freaking kidding me. I mean, this is, this one irritated the hell out of me. This was. The slabs are cantilevered. They're about 8 inches, 12 inches wide, and they're just wide enough to basically catch water and pigeon shit. And I mean, I said, what are you doing? I'm talking to the architect. What the hell are you doing? I mean, this is just wide enough that the occupants can stand on the ledge and jump to their deaths when they get their utility bill. What are you thinking? And then the architect tells me, well, I wanted the inner building to express itself. Architects, you know that this discussion took place because that's exactly right. I mean, this is exactly the comment that you're going to get. And I said, well, okay, I can see that, but what we could do is we could cut it flush, and then we could have continuous insulation, and then we could clip on. And nobody would know. And the response was, but it wouldn't be authentic. And so that's when I decided the architecture profession is not serious about energy. I think you're all a bunch of hypocrites. And you're using LEED to basically do the deal. And engineers, I view us as enablers. We enable that crap to happen because, see, we don't actually measure energy. We simulate it. See, because, it's like we're accountants. You know what accountants are like. What answer would you like, sir? We can give you any answer that you want. But commercial buildings are a joke. They're a disaster. But residential buildings are not. And the reason is in residential construction, we have, in the United States, an incredibly sophisticated energy monitoring system. Once a month, somebody goes to every house in the United States of America and reads the meter. And at the end of the year, you just add up the bill. And people are funny, you know. They know what they used to pay. They know what their neighbors are paying. And they know what you promised. And if you don't deliver, the retribution is vicious, brutal, and instantaneous. Right? Commercially, we don't measure anything. All we do is simulate. Well, I saved 30% with this computer simulation. I saved 8%, 8.4. There's always a decimal. Do you ever notice that freaking decimal? That's total nonsense. You know, if you're within 25 or 30%, you know, I'm like, whoa, that is amazing. And so I don't believe anything unless you measure it. And until we start measuring real energy consumption, I don't believe any of this stuff. Because I can give you any number you want. And here's to me what's important. You compare the energy consumption of your new building after a year or two, and the square meters or the square footage, and you compare it to a similar building in a similar location, similar occupancy, built in the 1960s. And if you haven't saved any energy, sit down and shut up, because I don't believe you. And right now, we're not measuring a damn thing. All right. This was not part of the presentation that I provided because I figured we'd get the hook, but I'll tell you something else. If I hear one more time that we're going to do a woofie simulation, I'm going to puke. Because woofie, you can get any number you want. And it's not designed to measure airflow. It's great for mass buildings. Europeans are famous for mass buildings, but we're hollow. We have three-dimensional complex airflow networks. You can't model that. So what do? Well, we rely on experience and fundamental principles. And it's like, no, but clients don't believe it. They like the decimal place and they like the computer simulation because of the beautiful graphical interface. And we've learned in our office, you don't get the dough unless you do the show. Repeat after me. You don't get the dough unless you do the show. Now, what we do is we do the show, but we give them a building that's going to work regardless of what the show shows. Do you follow? And it's real simple. And the motto is, don't do stupid things. So repeat after me. Don't do stupid things. And let's go through how to avoid stupid things. This is a stupid thing, right? I mean, the balconies are giant heat exchange devices. What we should do is cut the sons of bitches off, right? Throw out the windows, wrap them on the outside with external insulation, new cladding system, and clip the balconies back, and we're done. End of story. Come on, we know how to do this. I mean, somebody on drugs did this. It's not beautiful, it's just ugly. It's basically warming up the local climate of Chicago. It's trying to moderate so that the rest of the buildings don't need heating systems, because this is going to warm up the local heat island. And then look at this, you know, a double facade. Two, you know, we can't get one layer of glass, right? So let's have two. I call these people facadists. Why would you build a building inside of another building? Well, we're going to have magic air going between the two layers of glass, you see, the thermal effect. You know, and that moving stream of air is going to cool and reject that heat. Well, you know, I did the calculations. I mean, I used to be an aerodynamicist. You need subsonic flow. We would suck children and small animals off of the sidewalk, and we would inject it into low Earth orbit to make this freaking thing work. I mean, the stupider the concept, the more the architects and the owners will accept it. I mean, I don't understand. Is it because we don't teach math or physics in high school anymore? Hell, we don't even teach kids how to read, right? We don't teach them anything useful in high school, except how to feel good about themselves while they're unable to function in the modern world. Which is the only reason that I could think that an architect would accept an R11 radiant barrier paint on a concrete heat exchange fin in Chicago. I mean, does that? I mean, it's so funny. You have to laugh when you're not crying. But what the hell? This is great. And they want to retrofit this? Don't touch it! You know, I don't have a lot of glass and a whole bunch of rocks. Rocks don't burn. Repeat after me. Rocks don't burn. And structural engineers have figured out how these buildings should stand up. I mean, they don't fall down anymore. Structural engineers are very boring. You know why? Nothing ever freaking happens. Buildings don't fall down. 100 years ago they fell down. Not anymore. An extroverted structural engineer looks at your feet while he's talking to you. Right? Right? You want excitement, talk to a mechanical engineer because nothing works there. You know? Us mechanical engineers in all these glass buildings, we're professional turd polishers. We're trying to compensate. Here, make this efficient. It's too late. Right? That's why we have personalities, because nothing works. This is really awesome. Don't touch this one. This one, you know, take a rock. Throw stones. You know, that LEED award-winning building behind the church per square meter, the church wins. Right? Too much glass? Duh. All right, so, okay. Now we come to the regularly scheduled presentation. This is like therapy for me. Okay, thank you for... Some people drink. Some people go to a psychiatrist. I mean, I'm an engineer and I married an architect. Oh my God. The therapy bills were incredible. We're going to have children, and both associations contacted us, forbid us from having children. They were worried about the nature of the offspring. We had a daughter, and she became an attorney. What can I tell you? All right, so what is a building? It's an environmental separator. Its function is to keep the outside out and the inside in. That's it. That's the deal. Back in the day, like thousands upon thousands of years ago, our environmental separator was, you know, hundreds and thousands of miles, right? That was the environmental separator. We allegedly grew up in the grassy plains of, you know, primitive Africa, and we happened to like 70, 75 degrees Fahrenheit, 35 to 45% relative humidity. And, you know, the environmental, we didn't need any environmental separation except to keep the animals out, right? But we couldn't colonize the planet without basically creating and shrinking thousands of miles of environmental separation into a couple of feet, a couple of inches now, right? So that's what a building is. In the late 1940s, early 1950s, the rules of environmental separation were defined, and here they are. This is what it needs to be. This is what a building needs to do to become an environmental separator. I mean, it has to be beautiful. Okay, we got that. And we don't want it to fall down, and we don't want it to burn. Okay, so, you know, this fire, structural stuff, beauty, you know, I'm assuming we're smart enough to figure that out. But here are the rules. When somebody asks us to evaluate a building enclosure, this is the list. Does it control heat flow, airflow, water vapor flow, rain, groundwater, light and solar radiation, noise, vibrations, contaminants, environmental hazards and odors, insects, rodent and vermin, fire, strength, rigidity, durability, aesthetically pleasing, and affordable. That's how you evaluate a building enclosure. Now, some of these we're really, really good at. You know, the important ones. You know, they don't fall down because that's like a really big deal. They don't burn. That's a really, really big deal. We're pretty pathetic with some of them. And every generation wrestles with one or two on this particular list. Our generation's problem are heat flow, airflow, moisture flow. That's what we're struggling with. I mean, hell, we solved the fire problem after that cow kicked over that lantern in Chicago. Remember the Great Chicago Fire? It's not like we didn't know that a city would burn in North America. London had burned 3 times by then, Rome once. America was due. You couldn't build that way with that type of construction that close together. It was going to happen, we knew. The very next year, Boston burned, but nobody ever remembers the Boston fire because Boston always finishes second. So the building codes have handled fire very well. We had earthquakes and hurricanes, and Hurricane Andrew really got us a wake-up call, and we fixed the codes. And then the Northbridge earthquake shook things up, literally and figuratively, because it didn't behave like we expected it to, and things changed. So we're pretty good with the fire. We're pretty darn good with the structure. And now we're dealing with the energy and the water and the heat and the moisture. And we're struggling with it, but we're beginning to figure stuff out. And so I'm going to give you my version of what I think is important, but important in the context of this bigger list, because we've already done really good stuff with fire and structure and plumbing and sanitation. Do you follow? In other words, we're now knocking off the stuff that's not important as the other stuff that we've already handled, because we're a reactive nation, not a proactive nation. Things get intolerably bad before we intervene, and then we intervene in a messy way. Winston Churchill defined Americans as a nation that can always be counted upon to do the right thing after all of the alternatives have been exhausted. and so we're doing the right thing. It's just that it's taken us a while to sort our way through it. So my focus on building enclosure is heat, air, and moisture, simply because the other more important things we're already doing extraordinarily well. We're doing them well because we did them badly. You think about that tonight in the bar, and that'll make sense. All right, what destroys buildings? Well, you take away the fire and stuff, you end up with water, heat, and ultraviolet light. Of the 80% of building durability issues that we have that aren't dealing with structure and those others, these three account for the 80%. And of the 80%, water accounts for 80% of the 80%. So if we wanted to worry about something, we'd probably want to worry about the water. Everybody with me on this? All right. So we need a little bit of physics. This is, again, for the architects. The engineers will never understand this because there are no numbers in it. So this is the second law of thermodynamics translated into something useful. This isn't, entropy and the heat death of the universe and all that nonsense. This is, okay, heat flows from warm to cold. Why? Because. Because it is. Because. You got it. It's because of the second law, but who cares? Because works. Moisture flows from warm to cold. Why? Because. Moisture flows from more to less. Why? Because. Air flows from a higher pressure to a lower pressure. Why? Because. And gravity acts down. There's one more rule that you need. Architects, raise your hand. Here it is. This is for you. You can't push with a rope. If you know that and this, you can get an engineering license in the state of New York. Not in Boston. You have to be a Democrat, too, in Boston. But, in New York. All right. So let's say that we accept this. And I'm suggesting it's a pretty good thing to do. We should accept this. This map has staggering implications for us, right? I mean, up north, there are only two seasons, this winter and last winter. I grew up in Toronto, home of the Maple Leafs. It's a hockey team that hasn't won anything since 1967. So it's pretty easy to work, to build in a cold climate. The moisture flow and heat flow is all from the inside to the outside. You go down to Key West, you can, see Cuba. Canadians like Cuba because there are no Americans there. So, well, these are good lines, okay? I mean, this is, So you're in Key West, right? And you're always air conditioning, and the inside is going to be cold, and the inside is going to be dry, so the moisture flow is always from the outside to the inside. So you build in the cold. Anybody can build in Canada because the moisture flow and heat flow is in one direction. Hell, anybody can build in Key West and Havana and even Miami, because the moisture flows and heat flows always from the opposite direction. But the most interesting part of the continent is in the middle, where things go in both directions. See, the United States of America is unique. It's the only industrialized nation that's dominated by air conditioning. So I was kind of laughing at you. Sorry, because you're struggling with the air conditioning. I mean, you know, Germans like to be uncomfortable and you're always heating. This passive stuff doesn't work in Atlanta. You can't conserve your way to dry. And the better you are at saving energy, the less your air conditioning system runs and the less it dehumidifies. So if you really do a job correctly, you're going to end up having to spend the energy on dehumidification. We learned this a long time ago. This guy by the name of Willis Carrier, he wrote it in something called a book, which is found in libraries. But they're very, very old books, and you have to ask a librarian, and that involves a social interaction, which is why young engineers never learn about this anymore. So Willis, the old guy, before he died, figured out that you had to separate the latent load from the sensible load. Everything we do to save on the sensible side means the AC doesn't run, so now we have to add supplemental dehumidification. And the biggest dehumidification load is ventilation. It would be colossally stupid to build a tight building and then over-ventilate it, wouldn't it? Nodding here would be a... Okay, nod, this is a good thing? And so we're really anal about tightness, and I think that's fabulous. But to not ask ourselves what the right ventilation rate is in most of the United States where we have humidity. See this, you know, dry part, nobody lives there. I mean, you know, you think about it, right? Nobody freaking lives there, so why would we build for places nobody lives? I mean, it makes no sense. So, you know, this ventilation and humidity load is going to be the thing that you're going to have to wrestle with. That's not part of my discussion. I'm just telling you that if we succeed, which I think we should, in building a tight enclosure with lots of thermal insulation and really, really good windows, the ventilation and the humidity control is the thing that's going to be keeping us up at night. And we should go back to Willis Carrier. He actually figured it out. It's that book thing. All right. This is where it rains a lot. All right, so let's think about this. We have hot, dry, hot, humid, mixed humid, cold, very cold, subarctic. These are hygrothermal regions. And then we have rain exposure regions, right? We have low and we have moderate, high, extreme. All right, so let's pick Las Vegas, Nevada. Las Vegas, Nevada is clearly a hot, dry climate, right? Let's compare it to Biloxi, Mississippi. Biloxi, Mississippi is hot, humid. Las Vegas is a low rain exposure, and Biloxi, Mississippi is a high rain exposure. So what's common to Las Vegas and Biloxi? Casinos. What the hell is wrong with you people? Don't you freaking get out? I mean, casinos. Casinos are common to Vegas and Biloxi. And here's the deal. The companies that own, design, operate, and maintain the casinos in Vegas own, operate, design, and maintain the casinos in Biloxi. And for all intents and purposes, they were built exactly the same way. You can't do that. They don't freaking work. Right? We discovered that EIFS face sealed works in Las Vegas because it doesn't rain. And putting vinyl wallpaper, which is a vapor barrier on the inside of an assembly, works in Las Vegas because it doesn't rain and it's not humid. But, you know, my God, now putting vinyl wallpaper on the inside of a building in Biloxi with a face sealed EIFS, and then putting a rooftop exhaust fan pulling all the air out of the building, you basically get a building that sucks with a condom on the wrong side. Right? And who do you blame? You blame the contractor and the subtrades. You built it wrong. No. How can you compensate for installing vinyl wallpaper in a hot, humid climate? You know, there's no amount of workmanship that will make that work, right? So when they fail, we blame the Irish. We used to blame the Irish because they were the immigrants, right? Then we blamed my family, the Czechs, and now we blame the Hispanics or any immigrant class because immigrants build our infrastructure, right? These are not workmanship issues. These are design issues. And we have to be respectful of the climate. This sort of highlights the difference between quality control and quality assurance. Quality assurance is figuring out what the right thing to do is, and quality control is executing it. We're phenomenal on the quality control. We're horrible on the quality assurance. If you do the wrong thing right, it's still wrong, right? Tonight. All right, so let's say that you didn't want to have to think about any of that. I mean, I teach at a university now, and I'm not allowed to fail stupid people anymore, because that would be discriminating against stupid people. See, we're all the same. So if you're an idiot, I can't say you're an idiot. I have to, pass you. So I've decided to make it really simple. I've said, look, let's design a building enclosure that will work everywhere so that idiots who I basically have to pass can design and construct them. Does that make sense? Okay. So this is it for idiots. All buildings need a water control layer. Everybody with me on this? And the water control layer is more important than the air control layer. So if you can't keep rain and groundwater out of your building, I don't care about air. I haven't got a call, oh, my air barrier is flawed. I get calls like my roof is leaking, my windows are leaking, my foundation is filled with water. Those are the calls that I get. And, quite frankly, the water thing is more important than the air thing. Are you with me on this? All right. Once you got the water thing under control, then you deal with the air. The air control is far more important than the vapor control. I don't want to hear discussions about vapor barriers and woofy and crap like that until we have air tightness. All right? Once I've got the air tightness, then I deal with the vapor control. And the vapor control is more important than the thermal control. The least important is the thermal control. But the thermal control is the easiest to specify. If it's not important and can be easily specified, the building code obsesses over it. R value this, U value this, lambda this. It makes me drink bourbon, which is actually a good thing. The code is least specific in dealing with the water control layer, and yet it's fundamentally the most significant, isn't it? There's good news and bad news there. The good news part is that the code doesn't deal with it, so you can actually do the right thing. Because most of the time the code is a consensus opinion of wrong things. Right? Come on, we're, come on. That's why I had hope with the Army. I mean, the Army could do stuff by making up their own code. Right? And which is what they did with the air tightness. Where's Alexander? Where is he? You haven't got the hook yet? Well done, young man. Well done. Yeah. Okay. So how would this look? Well, here's what the perfect wall looks like. And this isn't my idea. I wasn't even born when this came out. This is a guy by the name of Neil Hudson, who figured it out independently of a Swedish guy named Navander in the late 1940s, early 1950s. But the Swedes didn't read English, and the Canadians didn't read Swedish, and it was just nothing ever happened until the Norwegians took it across. And they said, "Whoa, this actually works." And then they wrote it in books, and nobody read it. Anyway, so here it is. So we have the structure, and on the outside of the structure we have the control layers. That heavy black line is the water control layer. It's also the air control layer and the vapor control layer. On the outside of that is the blue layer, which is the thermal control layer. And it's blue in this presentation because Dow paid me yesterday. Is there anybody for Owens Corning? For the right price, pink is a very attractive very attractive color for this. So, they wanted me to make it green, but the hypocrisy of the green movement is so great I can't deal with it because everything is freaking green. Hell, the cab driver driving me in was a green cab driver. It's such a meaningless term that you want to kind of throw up. Okay, so outboard of that is the cladding. And the cladding's function is to protect the other control layers from exposure to water, heat, and ultraviolet light. It's a sunscreen. And it provides aesthetics and physical protection to the other control layers. And we want it to be ventilated and back-drained. We don't want to caulk it. We don't want to seal it. The only time you put sealants on the outside is for aesthetics. I mean, why would you want to put a sealant to do something critical in the one location where it's most exposed to the damage functions, which are what? Water, heat, and ultraviolet light. You want to put the stuff to the inside, right? Nodding here would. See, because these 30-year sealants, there's a neat study. It's not yet published. It's coming out. We didn't do it, but I'm a reviewer and I'm not supposed to say these things. But I will anyway, because what the hell? What can they do to me? I've already been, irritated. Okay, so almost 55% of all sealants fail within the first 10 years, and 85% of sealants don't make it past the 20th year. I mean, they're temporary if they're on the outside. You put them on the inside, they'll last forever because they're on the inside. It's kind of one of those neat things that... All right, so this is the perfect wall. Oh, wait a minute. It works everywhere. Let's go to Montreal. Let's build a humidified, pressurized building in Montreal. I mean, let's build an art gallery with a famous architect in Montreal. They never freaking work because they never build this wall. But let's say that we did it. So you've got the worst possible exposure, humidified, pressurized art gallery. Oh, let's also have it attached to a hospital and a data processing center with a swimming pool. That was one of my class assignments. I said, look, we're going to build a hospital, art gallery, swimming pool, and put it on top of a ski mountain outside of Montreal. Design a building enclosure. Well, there it is. I mean, you think about it. This works. So the moisture flow and heat flow, air flow is all from the inside out and hits the black line, and what happens? Nothing. Nothing. Because it's warm. That black line has all of the insulation on the outside of it, so I don't have a change in phase. If I don't have it go from a vapor to a liquid, nya, 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 nya. That's, New Jersey for don't bother me none. What happens if I have a hole? What are the odds that those Quebecois, those syrup slurping, poutine eating, hockey playing Quebecois, what if they screw it up? Well, we don't care. Because it's going to blow through the insulation into the air cavity and be ventilated to the outside, and the wall goes, right? So it's designed to fail in a fail-safe manner, right? Not nodding here would. So this works. Okay, so let's move it now to Miami. So let's put it in Miami. Let's build Madonna's house. So the inside is cold and dry, and the outside is hot and wet. And so the moisture flows from the outside to the inside. It's going to blow through the cladding, blow through the blue stuff, hit the black line, and now what happens? Well, it changes. It condenses, right? It goes from a vapor to a liquid. But it's condensing where? On the outside. It's like rain. The wall goes, I don't care. It's outside my building. My control layer is outside what I'm protecting. Now, what are the odds that those sandwich squashing, cigar smoking, mamba dancing, Cubans got it right? Well, about the same likelihood of the Quebecois, so there'll be a flaw or a failure. And so what happens if I have a flaw or failure in that line? It's going to get into the structure. But as long as I don't put a barrier on the inside, it's going to go through the structure and into the air. And once it's in the air, this mechanical engineer can freaking deal with it. Yeah, I want to get that air to the coldest surface in the building. And what's the coldest surface in the building? The air conditioning cooling coils, where I'm going to convert it from a vapor to a liquid, and we're done. So as long as I don't have vinyl wall coverings, I don't have impermeable finishes like epoxy paint, I'm good to go. So I put my defensive line on the outside. When there's a flaw, get the hell out of its way and let it go and get it out of the darn building. But here's the rub. I have to have it dry and cold in the building for this to work. Now, if I've done a really good job on my thermal loads, the air conditioning system isn't running, so it's not dehumidifying. So I need to make it dry, and so I need to have a dehumidifier. Now, here's a little lesson for you. Energy recovery ventilators don't make it dry. They maintain dry, so they will only work in conjunction with a dehumidifier. So you need a cooling system to make it cold, and you need a dehumidifier to make it dry, and then you maintain the cold and dry with the energy recovery piece. But you need all three. And if we've done our job really well, the absolute smallest is the cooling. But if we're really good at it, the biggest hunk of energy is going to be on the dehumidification, and if we overventilate, we're screwed. Does that kind of give you a... So this balance between ventilation and underventilation and overventilation is the most significant energy environmental decision you're going to have to make, because that's what saves the walls. Does that give you a... All right. So it works in Miami, works in Montreal. What about Memphis? Works in Memphis. How about Muncie, Minneapolis, Mojave, Monterey? It works everywhere. The only thing you have to decide is how much thermal resistance you want. And here's my answer. I've been doing this for 30 years. Whatever you think the right answer is, double it. Because I was wrong in the 80s. I was wrong in the 90s. Just talk to all of my ex-wives and girlfriends. They'll give you a list of how, well, we weren't talking about thermal resistance, but I was wrong about that too. All right. If I take the perfect wall and I flip it one way, I get the perfect slab, and I flip it the other way, I get the perfect roof. This is another aha moment. Ah, the physics of walls, roofs, and foundations are the same. So the perfect roof is a protected membrane roof. This actually comes to us from the old Soviet Union and Romania in the 40s, if you want to go back far enough. Oh my God, the membrane's right on the structure underneath all of that insulation. We should put it up at the top, because if we put it at the top, it's easy to get at to replace. If you put it there, you have to replace it. Right? If you put it underneath, you don't have to replace it. Now, if you replace the ballast with dirt, grass, and a goat, that would be a green roof. Right? I think green roofs are a really stupid idea for energy reasons, because dirt isn't insulation. If it was, we'd put it in walls. It's just freaking dirt. And insulation is cheaper than dirt. And grass isn't a very good membrane. It's not very reflective unless it's green. And to make it green, you have to water it. Are you kidding me? Putting water on the top of your building? The whole idea is to get the frickin' water off the top of your building. Are you an idiot? But you know, they're beautiful. And so I love green roofs for the right reason. Architects, where are you? Give me a green roof for beauty, and I'm going to be there with you every step of the way. But don't give me all of the nonsense that it's environmental and it's sustainable and the heat island effect, and I want to store water on my roof. The only reason the city planners like you to store water on your roof is because they've not invested in civil engineering infrastructure in the last 50 years. Rather than building sewers and roads and bridges and maintaining our infrastructure, they're supporting, you know, all of these artsy-fartsy groups. Give me a freaking break. Do your job. Don't, you know, waste money on the other crap. Give me, you know, and now we're trying to say, well, okay, put the private sector in charge of this, because we won't let you have the water that we should have been handling as a municipality. This stuff drives me crazy. But beauty? Yeah. All right. Flip it. We've got the perfect slab, right? I got dirt, stones, insulation, control layer, concrete. God, I love it. Now, in California, they're idiots on many levels. But one of the things that drives me crazy is they put a layer of sand between the membrane and the concrete. This is, that's the dumbest thing in the world, because what ends up happening is it ends up being a sponge. It gets wet and it's not capable of drying. So what you want is you want to put the concrete directly on the membrane so there's no reservoir. Think, oh, well, the concrete will curl. No, it won't. Just use the right water to cement ratio. The magic water to cement ratio is 0.5. At less than 0.5, you have no bleed water. We typically ask for 0.45 to give us a buffer, because what we want is 0.5, but we ask for 0.45 to make sure this doesn't happen. Well, you can't put concrete right on plastic in California. I say, you guys, how stupid are you? Across the street, there's a 2-story building, right? Yeah. Well, you have a fluted metal deck, right? Yeah. Don't you put concrete right on the fluted metal deck? Do you put a layer of sand in the flutes before you put the concrete? Well, no. Well, how does it work? The laws of physics clearly change between the first floor and the second floor then, because on the first floor, I have to put this freaking sand layer, but on the second, I don't. You're tricking me. It's easy because you're an idiot. See, this only happens west of the Mississippi, and I'm convinced on the Mississippi River there's a fence that prevents ideas from going from one side to the other. Okay. So let's take the perfect enclosure and put in the perfect wall, the perfect roof, perfect foundation. Now we have another aha moment. You ready? We got to connect them. Yeah. And how we connect them is magic. We connect the water control of the roof to the water control of the wall to the water control of the foundation. Then the air control of the roof to the air control of the wall to the air control of the foundation, and then the vapor to the vapor to the vapor, and the thermal to the thermal to the thermal. I was taught this in 1979. I was told to do design reviews, take a colored pen and trace it around your drawing set, and wherever the pen leaves the paper, you've identified a discontinuity. I was kind of neat. I looked at the Passive House book and I saw that you stole it. Good idea. Continuity of the control layers. That's the magic. And, you know, we get paid a lot of money to do this. It's amazing. Everybody can do this on their own. In fact, it's even easier. You don't actually have to do the whole building. Failures happen not in the field of a roof or a field of the wall. They happen where roofs meet walls and where we have penetrations. What's the most famous penetration of all? A window. Think about life as a window. This is the Zen part of the presentation. Right? A window has to do everything a wall has to do and more. It has to handle water, air, vapor, and heat, but it also has to handle radiation, right? You want the visible light portion of the spectrum to be admitted, but you want to exclude the ultraviolet and the infrared, right? That's why we call them spectrally selective. And every now and then, some lunatic expects to be able to do what with the window? Open it. Well, no wonder windows are so damn expensive. We ask so much more of them, right? But we've got phenomenal windows today, right? We have windows that handle all of those control functions. So how come we have more problems with windows today than we've ever had? Well, 2 reasons. And this is, I'm only speculating here. One is the window industry are idiots. I mean, wouldn't it be neat if a window came out to your job site that was labeled and said, this is our water control layer connected to yours. This is our air control layer connected to yours. This is our vapor connected to yours. This is our thermal connected to yours. I mean, I've been doing this my entire life, and I have yet to see a window come out labeled that way. And I don't even see it in the instructions. And when I call them up, they say, well, we'll get back to you on that. Well, then I don't trust them, right? If they can't tell you right off the bat what is their water control layer, you know you're in trouble. And I don't even trust them anyway, even if they claim to know. So in our office, we collapse all of the control layers on the innermost part of the glazing system. So we wrap the window openings with the water control. So when the window system eventually fails, the consequences of that failure are directed to the outside. A leak is not a leak if the client never sees it. Repeat after me. A leak is not a leak if the client never sees it. So that's one problem. The other is we've been relying on one person to do this the last 40 years. And I've been looking for him to get rid of him. His name is By Others. He shows up on all of the specifications. Window installation, by others. Shop drawings, by others. Dimensions verified, by others. Don't let this SOB on your job site. All right? You want to know who's responsible? Look in the mirror. That's who's responsible. All right, we're famous for building these square buildings, right? No, we're not. Those red circles are attorneys' targeting diagrams. Right? Because that's where we have the three-dimensional connection between those control layers. Right? That's where the failure is going to happen. And they're complicated. And you never see them drawn three-dimensionally on the job, on the drawings, right? Okay, I'm part of an architectural firm. We have 30 employees, and I know how many architects here. I'm going to let them in on a secret on the architectural business, okay? First of all, it's a business. For the rest of you to realize, it's a business. And the profitability of the business is dependent on getting the drawings and specifications out in a timely fashion, because your draws, your financial draws, are based on percentage completion of the drawings, right? You know, if your conceptual drawing sets, your 50% completion, your 90% you know what I mean? So the idea is always a race to push the drawings and specs out the doors as quickly as possible. Well, it takes you roughly 3 times longer to draw a 3-dimensional section than it does to do a 2-dimensional section. And so when, you know, most architectural firms will take the section such that it misses every one of those circles. Right? Nodding here. And who does the drawings anyway? Is it the most senior and experienced person on the firm? No. It's the intern. I actually lied. My daughter isn't an attorney. She's an architect. She did it to defy me. But I love her. And so she just graduated, and the first thing they gave her to do was to draw details. And the answer was, well, okay, this is what we did 5, 6 years ago. It's in the file. Put it on this drawing set. Right? That doesn't freaking work. You know that doesn't work. But, you know, that's who it is. And so the information is either incorrect or missing. And so you're out at the job site, and there's no information to the contractor or the subcontractors. And Guido talks to Luigi, talks to Lurch, talks to Betsy, talks to Jose, and they say, what do I do here? Just caulk it. Right? The universal answer, building science in the tube, is caulk it. We call it the caulk and walk strategy. And I'll tell you something else. Some of these details are too difficult to actually draw up. You actually have to do a mock-up. So we are absolute passionate believers in mock-ups. If you're going to put in 200 or 300 windows in a project, or replace 200 or 300 windows, you should all get together and do one together and figure out whether it works before you do the other bunch. Because this is complicated. Nodding here would work. All right, so here's the 3 walls with some more meat on them. This is the commercial wall. I'll show you the institutional wall. Then I'll show you the commercial wall. Then I'll show you the residential wall. If I was going to build a museum or a hospital, or I wanted to pass on a building from one generation to the next, this is what I'd do. I'd build it out of concrete and rocks, put a fully adhered membrane on the outside, lots of insulation, an air gap, and a cladding system. That insulation could be anything. It could be extruded polystyrene, expanded polystyrene, rock wool, fiberglass. I don't care. They all work. For institutional buildings, I happen to like fluffy rocks. Why? Rocks don't burn. And on the inside, I put sheet rock because rocks don't burn. And I make sure that the wall can dry out and the wall can dry in. And I can build it anywhere. Well, not everybody can afford this, so you build a commercial wall. Steel studs. And all the control layers are on the outside, so you put gypsum board without paper and the same control layers, but no fluffy stuff in the cavity. Because putting fluffy stuff in a steel stud cavity is a thermodynamic obscenity. If I put an R19 bat in a 5.5-inch steel stud wall, I lose 85% of the thermal resistance. It's effectively R4. That's because steel is 400 times more conductive than wood. I know this because I've never seen wood wiring. I've never seen a wood frying pan. Well, I did once. And so the only way to deal with steel framing is to insulate it where? On the outside. So this continuous insulation is a big deal. I learned about this as a child growing up in northern Canada, as all Canadian children learn. In Canada, when we were young, when it got cold, we learned to pull the sweater over the outside of us. We didn't eat it and shove it into our ribs. So, I mean, look at this. This is, the most efficient way to suck energy off of an enclosure. So steel is not green. I laugh about it. Oh, it's sustainable. We recycled the Pintos and the Corvairs in it. Okay, don't eat your sweater. So, I mean, whether this is insulated internally or not is irrelevant, because if we built two side by side and we measured them, we wouldn't be able to tell the difference in energy consumption within the experimental error of the measurement procedure. But, a little bit of continuous insulation on the outside is phenomenal. A lot of continuous insulation on the outside is even more freaking phenomenal. But none of that matters until you get the water control, the air control, and the vapor control. See, we don't want holes in the water control layer. We don't want holes in the air control layer. We don't want holes in the vapor control layer. And we don't want big holes in the thermal control layer. And the biggest holes in the thermal control layer are windows and thermal bridges. So get good windows and deal with the thermal bridges. But deal with them after you've handled the water, air, and vapor. Are you with me on that? This is not complicated. A wood building, you can insulate the cavities because wood is not conductive. Now, this works everywhere, with the stipulation is that the ratio of the insulation to the outside of that black line to the ratio of the insulation on the inside of the black line depends on where you are. If I'm in Montreal, I want 80% of the insulation on the outside and 20% on the inside. If I'm in Houston, I can live with 10% on the outside and 90% on the inside. So the farther north I go, the thicker I need to make the continuous insulation relative to the interior insulation. But this is only an issue in a non-conductive assembly. If we're dealing with wood, wood is good. It's self-replicating, carbon sequestering, micro self-replicating nanotechnology. That's wood. I'm trying to sex it up so that we actually, wood really is good. And good luck with that. All right, so a couple of examples. This is our water, air, and vapor control layer. You can tell an engineer was involved because there's no windows. But there was an architect because of the stupid curved roof. On the outside of this is the cladding system. And the continuous insulation. There are 5 different claddings so that the building could qualify for an architectural award. But that's a cynical comment that's the architects are going, well, yeah, I can see that. And see, it was meant to be funny and ironic because you like complexity, and I hate complexity. This has got windows. Notice how the opening is wrapped into, or the openings are wrapped with the water control layer and vapor control layer, right? Notice how the windows are, the openings are notched so that when we put in that window and it leaks, the water is directed to the exterior. On the outside of this, we have continuous insulation, and we have granite. This wasn't one of our projects. I took this in 1989. I couldn't believe it. I just moved to Boston. I saw this, and a little tear formed the corner of my eye, ran down my cheek. I was like, my God, Harvard, who knew that, Harvard could actually do something useful? And so how many granite panels? There are about 5,000. How many joints? 10 to 15,000 joints. And what are the odds that Igor, Guido, Lurch, Luigi, Manuel, Bubba, Betsy, Betty, and Jose are going to be able to caulk and seal 10 to 15,000 joints and have them installed on a warm, dry, dust-free surface? 0, but we don't care. Because, if all of the sealant fails, the building actually works better, doesn't it? Because I get more air circulation behind the cladding. So as this building ages and gets ratty and more disgusting looking, it actually performs better. And this is the same line I'm using with my wife. So here's our steel stud building, dance glass gold. Notice we patched the membrane at the corners because that's the weak link. And we found over the years that membranes don't stick to furry stuff unless you have a primer. So we've learned all about this stuff, and we've learned that we have to terminate the membranes. If we don't, they peel away and they fish lap. Just ask MIT and Frank Gehry on that building. So you have to caulk the top edge of the membrane if it's reverse lapped, or you have to tape it. But we learned. I mean, you screw up. Over this goes the insulation in the cladding system. This is my version of the Rainbow Coalition, right? The color doesn't matter here. We don't discriminate. I have to be careful with that line, don't I? Whoosh. Just don't call it a slut. So don't do stupid things. The problem here was they ate the sweater. They should have put on the outside. But I didn't care about this because this is MIT and they turned me down as an undergraduate. So, but this is a bigger problem. This is Logan Airport, Terminal A, and they've got the control layer, the water, air, and vapor control layer, but it's vapor closed, and they ate the sweater. The insulation needed to be on the outside, and it would have been a trivial thing to do it during construction. It wasn't like they were short of money, right? But they made the project green by putting PV panels on the parking garage. That was a cynical comment that, okay, you got it. All right, draw a map. Then I'm going to close on this because every now and then something magnificent happens. This is a Smithsonian. This is the Museum for the Native American. And you see the Capitol dome behind it. And this is one of the most beautiful buildings I've ever seen. It's been done for a couple of years, but you need to go have a look at it. And they did it right. They had a structure with concrete and block, a continuous water control, air control, and vapor control layer. On the outside of it, they had rigid insulation, an air gap, and a cladding. They did it beautiful. I mean, it takes your breath away to see a stunningly beautiful building that's going to stand the test of time, that's ultra energy efficient. And so the message is, don't do stupid things, don't give up on beauty, follow the physics, and we'll be all in good shape. Thank you.